Okay, Tim. All right. All right, this is installment number 12. Okay. I know, you're happy. Right. Okay, so I'm going to let me tell you, we've had some nice press in the last couple of weeks, because it turns out I also do research and stuff. And let's see, so let me show you that. So we have a piece in the New York Times today, which you can check out. It's by John Tierney, who's kind of a very well-known science journalist for the New York Times. There's an ad for underwear next to it, but anyway, so it's a good piece. It's about this finding we have now that 10 languages and 24 corpora in those languages, major languages, I've told you about this, have a positivity bias. And it really sort of focuses on the news because it's a bit of a surprise for news, but it turns out to be true there. So he was on CBS this morning with Charlie Rose and Gayle King, and we did an analysis last night, which destroyed 4 or 5 hours. It was this bit here. We did, right? So we got transcripts they sent us transcripts, and we looked at the words they used and compared them and so on. And all right, lots of fun. So that was, you can watch that clip, 3.5 minutes. And what else? Yeah, and we did this, and we did an analysis for the New York Times. So it makes sense. Society's up at the top, right? Wedding and graduation and all these good things, and foreign is down the bottom, which means war and all these terrible things that happen. But generally, and that's getting pretty close to the lowest thing we've seen, I suppose. It's just above neutral in terms of this positivity scale, and as you go up, it becomes kind of more and more, well, it makes sense. The spread is pretty sensible. Anyway, a thing to play around with, these word shifts over here are these kind of elaborate wordles, if you like, or word clouds, and there's all sorts of good stuff in here to play around with. This was built by one of our graduate students, Andy Reagan, who's amazing, so this is great. Anyway, so that's good stuff, good stuff. All right, back to the horrors of matrices. So we're going to find more amazing things inside matrices, and today we get to expand ourselves, our brains, into some really good territory. Okay. Get rid of that. So we're going to talk a little bit more about finding bases for the column space of A. Remember I said there were 3 ways to do it. They become more and more spectacular as we go along, but there's a kind of a level of understanding that you get from each one. Right, we're loading it in. Why the dimension of the column space of A is the rank R. Right, so M, number of rows, N is the number of columns. Rank R is this thing we uncover from row reduction, which you're all champions at now. It pops out. It's the number of pivot columns, and so that's connected there. And then we're going to get to what I'll call the final frontier, row space, and this thing full of nasty things. Left null space. It's the known unknowns, right? So not quite Rumsfeld's level of stuff, which is very important, right? The unknown unknowns, they're very important. You want to somehow characterize what you don't know. All right, we'll get there with known unknowns. Okay, so that's what we're doing today. And we'll get to this, that the transpose of A, this benign little thing that we do with matrices. Just flip them over, right? Take a little transpose, not a big deal. There's this one way of flipping matrices that matters, and this is the reduced row echelon form of A transpose. That, and so this character plus the reduced row echelon form of A, everything is in here. So this is kind of a magical story. When I say kind of, I mean not the magic you're used to. All right, it's good, it's great, very nutritious. Math, okay. So it's wipe on, wipe off sort of stuff, right? We're getting there. This is done. Okay, good. No, select from these sheets in front of me things to say. We're still going to have our friends. We're still going to talk about these characters. I'm giving them names. Okay, off we go. So our 2 stars are still on this episode. We still have this character, 2, 2, 6. I'm going to write it down again. 4, 4, 12. And 3, 6, 12. 4, 10, 18. Right, and so this is 1A, and I'm going to call this one Fezzik. I'm going to give them names. This will be Fezzik, and we have the reduced row echelon form for this character was 1, 2, gosh, this is hard, 0, minus 1, 0, 0, 1, 2, and 0, 0, 0. And then we had this other little beast, which we can kind of take apart and look at much more easily. This is a bit more complicated. This is kind of a giant, if you like. And then we have this little beast reduced very quickly to this one. We'll call this one Inigo. Okay. Right. Write that name. Okay, you can see it's unraveling, all right, people? Good. Sorry. Okay, column, right. Last time we showed last time, right, previously in Matrixology, we showed the dimension of null space of A is equal to n minus r. So I'm not going to go through this again, but this is the number of columns in A. I'm going to say it again. This is the rank of A. And this is equal to the number of free variables. We had an explanation for why this is. Right? Okay, so we got that one. Lots of things will add up. Okay, so we've got this. So next, we want the dimension of the column space. We want to show this equals R. So dimension, once again, is the number of vectors in a basis for that subspace. So again, the dimension of a subspace equals, so we're kind of just recapping everything, equals the number of vectors in any basis for that subspace. That's awesome. All right, that's good. Right, so R2, we have I hat and J hat. That's what we kind of run around with because Descartes said it. Okay, so we're doing that. But we can have these two vectors, right? Yeah, that would work too. We talked about this. If we have three vectors, we need to probably get rid of one, right? These three vectors, we can take this one out, or this one out, or this one out. We'd still be able to describe our basis by any linear combination of those two remaining vectors. Works. Put my sheets on it. It's very dangerous. Okay, so good. Good. Okay, so let's. So here's a funny thing that happens when you do. I mean, everything's funny. When you do row reduction, an odd thing that we have not. I may have alluded to it. So here's a peculiar. There's hot air blowing on me, which in principle is a good idea. But okay, peculiar thing that happens. Right, when we enjoyably, right, we're usually singing songs from Sound of Music, enjoyably perform row reduction. Right, so here's an odd thing that happens. So we're doing row reduction, we destroy what's in the columns, right? So that seems fair, right? So one, we sort of destroy the columns, the columns. So let's look at Fezzik over here. Fezzik, no, I'm getting confused, Fezzik. So this one ends up as, right, so column one is 2, 2, 6. You know, this eventually becomes, through row reduction, this glorious process that monks use in their devotional activities, 1, 0, 0. Because these are not the same columns, they're different, right? So the column space of the reduced row echelon form of matrix, generally speaking, is not the same as this column space. So we observe the column space of A is generally, right? We may not have to do any row reduction, so it's the same. Generally not the same as the column space of, this is a weird thing to write, of the row reduced form. Right? We can't even, there's not even if you like, a z or an x, right, a y3 variable. There's nothing here. We've got these vectors 1, 0, 0, 2, 0, 0. These characters can't build, right? We can't build any numbers here. But, so column spaces change, but the relationships between the columns stay. So this is kind of, but, it's a miracle, but a miracle. It's not a miracle, it's math. Okay, math. Actually, math. In fact, is that the relationships, this is two relationships between the columns, this is glorious, between the columns of A are the same as, so let's look at Fezzik here, the same as the columns, those, there should be those for R of A. So, Fezzik. Who likes to make puns? Okay, likes to rhyme. Fezzik likes to rhyme. Okay, so look at this. So column 2 is, how is it related to column 1? It's 2 times it. Still true? Right? And we can see them more easily over here. So we'll write down some examples. So column 2, good, that was a good one. Column 2 is equal to 2 times column 1, right? For both, for A and R sub A. So we're just observing things. Let's look at a couple of others. Here's one, this will help us a little bit. So column 4, this is let me label these things while we're here again. These are pivots, yes? Pivots, free, yes? Pivots, free. The free ones we can build out of the pivot columns in kind of nice ways, right? So that's usually true. So let's see. So the fourth column, column 4, is some multiple of column 1 plus some multiple of column 3. Let me say it like this. So see if you can answer what they are. Just write them down. What did I do? What's the word I keep using? Fezzik? Just a random Princess Bride reference. That's it. Got nothing to do with it. Fezzik is big. Andre the Giant. Let's go for what? Okay. And this is You Killed My Father. Right? The Six-Fingered Man, Christopher Guest, no? Oh, God. I'm just amusing myself, and I'm sorry if that's confusing. But it is easier to call this large one something. So. All right, so homework is to watch The Princess Bride. It would take a miracle. Okay, all right. Trying. Okay, so let's see. Right, so did you get this? I will clarify other things like this, I'm happy to. So it's very nice, right, because this is actually a basis. This is what we've done when we made our pivot columns. We've made the standard basis vectors for Rn. That's I hat, and we made a J hat. We will always make I hat and J hat and K hat, and then sort of horribly L hat and M hat, but it doesn't work. We went IJK and 4 dimensions too hard, so we just get it. But because we're always building those things, we can see. So this is -1 times the first one, and this is 2 times the second one. We're gonna sort this out. This is great. So this is column 1, column 4. So this is, let me write it here for the reduced row echelon form, where it's easy to see. And this was -1, 2, 0 equals -1 times 1, 0, 0. Plus 2 times 0, 1, 0. So again, happy to repeat it. So the pivot columns of A, of R sub A, sorry, the reduced row echelon form, are always the columns of the identity matrix. Number of them, it depends how many there are. And let me add to that right, and so, right, 1, 0, 0 equals I hat, and 0, 1, 0, J hat, etc. These are, so this is the standard basis for R3, and in general, the pivot columns, so there are R of them, the R pivot columns, so the monks have led us very well. These are good monks. Got to be careful with monks. R pivot columns, it could be a death cult for example. So R pivot columns of R sub A form the first R basis vectors. I want to say this, standard, that's the word. Standard basis vectors for, what is it, RM or RM? It's M or N. Monkey or Neptune. Monkey or Neptune? M or N? Or R, M. Cool. Good. Right? So this one of course just has 1, 0. Right? I hat in R2. Yep. Cool. So we're building. So we're making these basis vectors, and it's really easy to make the free columns out of them. Very easy. In fact, it's just sitting there, right? This is essentially, yeah, -1, 2. That's it. Right. So easy. Okay. Good. Good. So this is in RA, so it's easy to see here. I know, always dangerous to say these words. So this was easy to see. Easy to see. Classic nonsense from mathematicians. Trivially, obviously, after 40 minutes of staring out a window, you say, yes, obviously. All right, but let's see that this is also true. But it is hard to see here. It's hard to see back in the original physics. So A, let's check it. So the first column, so this is, column 4. Not to be confused with column Firth, who has nothing to do with this. 1 times, this was column 1, and it's +2 times column 3. Let's look. So 226 and 3612. 226 and 3312. Am I saying the right thing? 3612. 3612. Trade me. And 41018. Is that true? Let's see. 4. So this is a -2 +6. That's good. And then we want a 10. So there's a 12 -2. And then we want 24 -6 is 18. Cool. Groovy. So that's done. So this is not easy to see. Not easy to see. Unless you're very special people from A. Let me write it here. Easy to see in the reduced row echelon form. Not easy to see in A originally. So what's going on? We're destroying the columns, but not the relationships between them. Why is that true? That's bananas. So, okay, good. I think I've said these things. Good. Yes? 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 All right. So the key observation is point is when we perform row operations, say it again, we do not change the relationship, or we can't, relationship relationships between columns. Right, so Fezzik, we'd start off with, that's too long, so maybe we shouldn't do that one. So let's say the Inigo character. So we have this 1, 2, 2, 4, 1, 2. We do one step of row reduction. Always the same thing, because we're good people, right? So R2 prime equals whatever row 2 was minus something times row 1. Always the same. And it's 2 divided by 1. We're always doing that, because the monks told us to. They promised. So if we do that, the new row 2 is the old row 2 with some, we're just adding rows to each other, some combination of rows to each other. So whatever is true between these columns, right? This is 2 times this one, this is 2 times this one, that's going to be preserved. And if you double a row, 2, 4, 2, or 10, 20, 10, nothing changes between the columns. Right, so you can see it here. So both of these both share the same relationships between columns, right? They exist, so they have to be true for each row. So i.e. true for each row for each row. Right, so when we say back here, column, the fourth column is some combination of the first and the third, then we're saying it's true for every row, right? It's true for the first row, it's true for the second row, it's true for the third row. So now if we just mess with rows, but by just multiplying the whole row by a number, adding them to each other, we can't change it, right? So linear combinations, because that's ultimately all we're doing. We're doing linear combinations of the original rows of A, preserve, must have same column, that's an H, have same column relationships. It's an emotional moment. How are we feeling about that? Let's see. All right, bit of a long walk, but there we go. That's truth. So this is a truth. This is a truth. I'll resume my silly photographing this thing. Okay, good. Awesome. Show myself. Okay. Good. Let's do it. Let's do it. All right. So, what does this mean for this whole basis business? Well, we have this nice story now that we're going to end up with some pivot columns. They're going to be basis vectors for our monkey, and that means we're going to be able to build the free columns out of those. So the free columns, in sort of a reverse of the null space, we can see those columns can be made out of these. We could get rid of them, and these are the basis. This is our basis now for this new column space. But because these relationships are the same back here, because the fourth column can be made out of the third column, the second column can be made out of the first column, we can get rid of those too. And say, these are the only columns we need for a basis. So let me say that again. So, observation by clever monks. The pivot columns, here it is, so the pivot columns in A, right? And these are determined by by finding the reduced row echelon form, these pivot columns form a basis. So there's a couple of things that are going to follow here. For C of A, the column space of A, they are a basis. So, right, so the Fezzik example, write it down again. 2, 6, 4, 4, 12, and then 3, 6, 12, and 4, 10, 18. This is our pivot free. So that means that these characters, so a basis for CA, this is our second way of doing this. And I'll note that this is the second method. We've already had one. This is our second method. This is a bit of a deeper thing. Basis for CA is just those two vectors. 2, 2, 6, the first column and the third column in this case. 3, 6, 12. Right? Obviously, we can make the first column with it. Right? 1 times that guy. We can make the third column. And because we understand what the reduced row echelon form looks like, we know, and it's going to be more elaborate for bigger ones, that the second column can be made from just 2 times the first column, and the fourth column can be made from these multiples of the first and third columns. This is a basis. And so from all of this, it follows that the dimension of column space is the number of pivot columns. So much excitement. So excited. All right, okay. Trying to adapt the language. All right, so, did I say it was a big deal? So big deal. Well, let's also do an ego as well, so a little character. Okay, an ego, so this is an easy one. 1, 2, 2, 4, 1, 2. Pivot, free. So this one, so basis for the column space here, oh, that's a terrible amount of things, is just 1, 2, which we determined before. We determined these things before. But this is a slightly different basis to the one we obtained before. It doesn't look the same necessarily, but it describes the same plane. Okay. So the big deal is that the dimension of column space of A, which is equal to the number of basis vectors needed to describe the column space of A, triumphant, there should be music, it's a funding issue, is equal to the number of pivot columns. Because the pivot columns form a basis, which is equal to R by definition. Okay, all right, so it's going to matter that little n minus R we had before, the R we have now. This is R as in pirates. It's a little bit of a pirate R. R. Okay. Okay, I know it can be hard to communicate small letters and numbers and things. Okay, 8. Okay. Terrible word. All right. Yes. So I think that is almost where we want to go here. Okay, so let's draw a big picture story so far. Big picture. We're going to have more of these as we go along. Big picture so far. There are all sorts of details here for an ego. Okay. It's going to look like this. So it's again 1, 2, 2, 4, 1, 2. So m equals 2, n equals 3, and r equals 1. The things we kind of know now are this. So there are, we can't quite say this part. Okay, so over here is Rn, and over here is Rm, which is equal to R squared, R2 I mean, and this is R3 in this case. And I think we can say these things. So we know that we have these from the other day. So there's a plane described, so this is going to be something like this. There's a 0 here. These two vectors are, let me draw it like this. This is a plane. This is, we had them the other day, -2, 1, 0. And these are, this one is 1, 0, -1. So this was a basis for null space, which we derived. Null space equal to -2, 1, 0, and I think it should be -1, 0, 1. Yes, sorry, -1, 0, 1. -1, 0, 1. This is previously. So these things, and over here is this guy. So this is where the x's live here. It's definitely going to be confusing. We're going to get there though. And then over here, column space is any multiple of 1, 2. So let me, in fact, I can actually draw this, right? So this is y1, this is y2. So a times x lives here. Right, the b's live over on this side. This is 1, 2. Let's do it like this. So here's a basis for, this is column space. Column space of A. This guy, any multiple of that. And somehow it points over here, so this is an x over here. We haven't quite figured, this is where we're going to get to today. So there's a point x over here, gets sent to some point over here. So A times x equals B, ends up in column space, right? Must go to column space. And an extra piece we have now is the dimension. The dimension equals R, which equals 1 with this character. And this one, this whole plane here, this is null space, and the dimension is equal to n minus r, which is 3 minus 1, which equals 2. So it's a plane. So, okay. Bananas, I know it's bananas. Everything, every multiple, every linear combination of these two vectors gets sent to 0. So this one gets sent to zilch. This is 0 over here. This one gets sent to zilch. So these are A times X, and we called it homogeneous, equals 0. So the null space vectors map to 0. Right, this will become more resolved, yes. Yeah, so because these things are, right, so good question. These things are real subspaces, so it has to go through 0. Yeah, so what we'll see is that null space, column space, and these two other magical spaces, whatever they are, if they're a plane in 3 dimensions or a 5-dimensional subspace in 20 dimensions, they have to pass through 0. It's a subspace condition. So for instance, 0 is always part of null space because A times 0 goes to 0. Yeah, so it's always going to tie it down. Yeah, absolutely. Sorry, absolutely. This could be all over the place. Yep, that's right. There's something about these guys that are off it, that are pointing in a different direction. And there are all sorts of points out here. So this one, this one, this one, these are all unreachable. can't get to here, you can't get to here, and you can't get to here. Anything that's not on this line, column space. In this case, column space is just a line. Column space could be a plane. It could be a 47-dimensional space inside 83. You can't make those. Again, these are so these are the combining weights. The x's are x1 times a1 plus x2 times a2 plus x3 times. Right, so let's write it here. In general, this is our little thing. This is x1 times a1 plus x2 times a2 plus xn times an. So there's some confusion. There are different ways to present this, but we're thinking about A sending x to B, which at the same time you can think of, right, that it is a linear, we're taking these columns in A and combining them. It's useful to think in both ways. All right. This will become more clear. Clear first, suffering. Okay, we must suffer some more. Okay, that's okay. Good. Big fan. All right, so any more questions about this horrible thing on the board? Yeah.
Do the null space vectors map to 0 vector or 0, 0?
Say it again.
Do the null space vectors map to 0 vector or 0?
To the 0 vector. Right, exactly. So A times, in this case, this blob. So it's A times a 3-dimensional, 3 by 1, ends up as a 2 by 1. Yeah, so this has lost its little hat. You can't see it. This is equal to, in this case, 0. And in general is an m by 1 0. Good. So it's sent to a special kind of 0. Right. Yes. Yeah. More questions? So happy, aren't you? All right, okay. Okay. Right, let's move on to these next subspaces, these other things that I promised you. Where dragons are. Monsters. Yeah. Right. 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 Let me add one thing for you, I guess, just to add. Right. So the big picture is basically saying, big picture encodes this, that A times, well, you know we can't do it. All right, we can't do it. All right. I'll get back in my box. I'm not going to do it. Okay, so you go over here. Very good. 2 more subspaces. Okay. 2 more subspaces. Row space and left null space. And ridiculously, left will be on the right, and the right null space will be on the left. Geometry versus algebra. So I'll clarify that horrible, confusing thing. All right. Okay, so first, row space. Why not, right? We have column space, so let's have row space. So it's a subspace. It's pretty good. This is where it really starts to cohere and become awesome. It's a subspace of Rn. Right? For Neptune, this is where the x's live, where the x's roam. So it's in there. And it's spanned, and so it's a subspace of N, and this is its definition. So it's spanned by the rows of A. Right, so we'll take, so e.g. we'll take Inego, right? So we're going to turn them into columns. So we have 1, 2, 2, 4, 1, 2. So the row space, I'll just write as row space of A in this case is equal to every combination. Let's see, we're in 3 dimensions. This is a 2 by 3. So it's every x in R3 such that x equals some multiple. I'll just put a C1. This will be better. 1, 2, 1 plus C2, 2, 4, 2. And C1 and C2 are elements of real numbers. All right, so this is every linear combination of A's rows. And we turn them into column vectors, right? Because that's just how we define vectors. Right? We write as, that's an X with a hat, write as column. So you can see that this is not a great description, right? Because what is lacking in this description? Or what is being overrepresented, perhaps? How can we make this better? Yeah, we could just, this is a multiple of this one, so we don't need this, right? So, and in general, that's going to be the case. Let's get fuzzy, right? Very good. So we observe, how are we going to do this? Oh, yeah, okay. So we observe not a great description. Right, we can throw out, as we can throw out 2, 4, 2 to make a basis. A real basis. A real basis, not a wooden basis. Mixing the stories. Okay, so this is a real, so we can get rid of this one. It's any multiple of this will work. This is a spanning set at the moment. This is 2 bases, they span this space. Okay, so we're just kind of making this up. Column space is a big deal. Row space might be something that matters. So I'm just sort of introducing it like that. So all right, so find space sounds great. Right, we've got column space, so why don't we do this as well? But is row space meaningful and useful? Question mark. Oh. Right. Yes. All right. Yes. Right. Yes, for many reasons. Yes, for at least 6 reasons. 6 big deal reasons. I may have more in the great tradition of the Spanish Inquisition. All right, so let's see. So let's do this. So big deal number 1. Let's abbreviate that. So BD number 1, BD1. Okay, good. So this is going to be that if we have an X that is in row space, so in this case it's easy to see, it's any multiple of 1, 2, 1. Right? That's what it is. We don't have to do anything. Then, so big deal number 1. If X is in this row space of A, and I'm just going to write it like this, the row space, there's a space in there of A, and x is not equal to 0, right? X 0 is in there. It is a nice subspace. 0 is in here. C1, C2 is going to be 0. Then a times x is not equal to 0. So this is the first glimpse that shows you it's very different than null space, right? It's not the same as null space. So a times x goes somewhere, and this x in row space is very different to x in null space. X in the null space of A, right, where a times x equals 0. Very different, right? So we've got a different kind of beast now, right? The null space is part of, so we can, I'm going to repeat myself. Of course I will. All right, so let's do our example. We've got, I've written down what it sort of is, but let's do a better job. We have row space most compactly is equal to x element of R3 such that x equals c times 1, 2, 1. C is an element of R, right? That, just by observation. We have to figure out how we do this in general. Of course, the monks have laid excellent tracks for us, so we're going in the right direction already. They're trailblazers, which I failed to observe in the vault of backcountry on the weekend. Okay. Right. So we have this just by observation, right? Later, we need a technique later to get it. So what happens to, let's look at it specifically. A times x, in this case then, is 1, 2, 2, 4, 1, 2, times some multiple of 1, 2, 1. Right, so it's an arbitrary vector in row space, as we've defined it. What's that equal to? Very tiny multiplication. All right, so 1, 2, 1, 1, 2, 1. Right, so that's a 6. 2, 4, 2, so 2, 8, 2, 12. And there's a c out the front. So this is 6 times c times 1, 2. That vector lives where? Where does that vector live? Column space. It's in column space. So we now have this joyous moment where a times a vector in row space ends up as a vector in column space. Right? So must be and is a vector in the column space of A. Okay, good. Good. So in some ways, okay, well let's not say that. Okay, good. So we're starting to get the idea. So remember this business, x particular must live in row space. Right? We recall the general solution. General solution to, so awesome, to A times x equals B is x equals x particular, that's a terrible looking x particular plus x homogeneous. Right? And A times x particular equals B, and A times x homogeneous, A times x homogeneous equals 0. So null space, row space. We're going to see that these things beautifully carve up Neptune, Rn. Huge, people. Lots of work to get to here. Green. Okay. So this is maybe row space is always maybe row space. This is definitely column space, null space. Definitely null space. Maybe that's definitely null space. So it's a bit funny. It's a little bit strange, but the solutions to Ax equals B are actually in the rows of A. Right? They're actually in the rows of A. So the solution to any Ax equals B problem is some combination of the rows of A. Okay, so we have a lot of other things to say about row space, including how to get it. I know you want to know how to get it. The good thing is we've done all the hard work already. Figure out what to do with that. Okay, good. This is this. Where did I put it? 12, 13. Oh, yeah. I did write on this. All right. Okay, let's do it. Yes. Okay, so that's one thing. It's just an idea. Let's see. Okay, so there's a reason here. So Nope. Writing the wrong thing. We just said that. I'm going to say big deal number 2. Big deal 2 is going to be, this is a powerful piece. So any x in A's row space is orthogonal. All of these things fit together beautifully. Orthogonal to any x in, so it's a bit deeper than what we've said here, in A's null space. Null space. They're actually, so this means at right angles. So it's getting a bit stronger. All right, so the reason, very basic, is A times x equals 0. It means that the columns of A, the rows of A, and x, right, they have to be, the dot products of A's rows and x are all 0. Yeah? So the dot products, that's how we do matrix multiplication, of A's rows and x, if it's in null space, all equal 0. Kind of awesome, people. Okay, it's good. So let's go back to Inigo, who is also left-handed, 1, 2, and C1 minus 2, 1, 0. I hate to kill you. Minus 1, 0, 1. Let's see. It does. It's how we found null space, right? 1, 2, 1. Dot product with this. Yes. Right? 1, 2, 1. That's minus 2 plus 2. Gives you 0. So it'll be C1 times 0. And then 2, 4, 2, dot product with this is minus 4, plus 4, 0. Plus C2, and we get 0, 0 again. This is, this is just by construction of the null space of A. So that's funny. So this solution, these guys are going to be at right angles to each other, which is a kind of a good thing, right? So there's no wasted information, if you like. This one doesn't have any information that this one has. They're really separated. This is one of those things that will be, once you figure it out, it's like, oh, that's completely obvious. But pain first. Okay. Okay. Okay, that's pretty cool. All right, that's good. So they're at right angles. So column space will be at right angles to something else. A place full of evil things. Okay. Good, good, good. All right. Oh. Okay, big deal number 2. Let's go to number 3. Yellow does not come up. All right, so that's that one. That's very excellent. This is good. So, big deal number 3. So before we showed that we are, this long line up the start. Column space gets destroyed, right? The column space of A is not the column space of its reduced row echelon form. So from before, the column space of A is not equal to, in general, the column space of the reduced row echelon form of A. You destroy the columns if you start to do any row operations, right? Right? I mean, if A is equal to the identity, there are no row operations in the reduced row echelon form. This is what it is. So, but that's true. But now the row space of so many good things come for free with tofu knives. Row space of A, free set. Row space of A is the same as the row space of the reduced row echelon form of A. Huge. You can draw a little. This is yes. Hashtag yes. Okay. This is good because we've done that. We love finding the reduced row echelon form of A. We've got it. Someone hands us A, and we spit back the reduced row echelon form of A, and it's a simple structure. So let's go to our examples. Here you go. 1, 2, 2, 4, 1, 2. After very minor suffering, goes to here. 1, 2, 1, 0, 0, 0. Right, this is A. This is reduced row echelon form of A. Same row space. Right, so we did a simple observation that that's the definition of row space. It's every linear combination of these two rows as columns. Clearly, right, made this observation. It's the same as this one. Good, so it's clear. So okay, so row space of the reduced row echelon form of A is just clearly equal to any x in R3 where x is some multiple of 1, 2, 1. C is some element of the real numbers. Just there. We had to do one more little step when we first tackled this, somewhere erased or behind. And we made a little observation. But there could be 1,000 rows, right? And our brains will hurt. We'll feed it to a computer. I won't say that. Okay, so let's see. Incredibly funny thing I thought of. So let's see. So, Physic, our loyal friend. 2, 4, 3, 4. Let's write down again. 2, 4, 6, 10, 6, 12, 12, 18, Anybody want a peanut? 1, 2, 0, minus 1, 0, 0, 1, 2. Okay. Really? Okay, so so we have A, reduced row echelon form of A. Now it's hard to look at this and say, okay, the rows of this, okay, there's row space, let's do it. So this one would be any combination of 2, 4, 3, 4. Eek. So C, I'm just going to kind of write it like this, plus C2, 2, 4, 6, 10, 2, 4, 6, 10, plus C3. See, now we didn't have to go that far to get something that was not very obvious. And so C1, C2, C3 are elements of the real numbers. So this is every x equal to this character, this box. So this is opaque. Let's say it's opaque. Eek. What? We'd have to deal with this. What am I doing? We okay? Definition of row space, as we've just sort of said, this is what it is. Take every row of A, turn them into columns, and then take every linear combination. And so this is in 4 dimensions, right? So this is R4 in R4, and this is n equals 4. It is a 3-dimensional subspace of R4, which is a nightmare, right? R4 is an infinite. I mean, one way to think of R4 is a time series of universes, right? So this is just one of them. This still hurts a lot. Okay. So this is a 3D subspace of R4. That's not easy to see, but this one is every x. Magically, this is all zeros, so we don't need that. Every x equal to some multiple of 1, 2, 0, minus 1. Ooh, the monks. Thank you, monks. 0, 0, 1, 2. 0, 0, 1, 2. Nice. Good. Okay. Much better. So this is much better. We've argued before that this has this structure, right? So there's the identity structure is sitting in there. We know that's it. We know we can't reduce this any further. We can't make this vector out of this vector. This is a basis. There are 3 here, right? There are 3 vectors here, but one of them can be written in terms of the others, which is a slightly horrible thing. So in fact, have I got enough things in? Yes, I do. Right. Yeah. 2 times this vector plus 1 times this vector equals this one. Did I say the right thing? I think so. So we could get rid of this one. Right? So there's a redundancy here. Redundancy. This is a spanning set. This is really a basis. Basis for row space. Yes, it's good. This is opaque, it's a redundancy. This is just a, I'm going to write another horrible thing pointing to it, just a spanning set. Yes. So, row reduction, the reduced row echelon form has a basis for row space. Just sitting there. It's already been done. You can't simplify these anymore. I'm excited. Okay. This is magnificent. This is really magnificent. And so what else does it mean? So it also means okay, big deal. Yeah. So I'm going to have 50,000 big deals. Okay, so big deal number 4 follows from this one. is that the reduced row echelon form of A contains a basis, a delightful basis for R for A, for A's row space. Right, we thought of this before as U. This is it's a reduced row echelon form. We know we can rebuild these guys, these rows out of this. We're just adding and subtracting things from each other. Right, so all rows in A can be made from rows in R sub A. Yes, awesome, right? Maybe? How we doing? What do you think? Is it working? Airtight, right, okay. Okay, people, all right, more photos. So, that's good. So what's the dimension of this subspace? So U and M moment, people. U and M, what is it? 2. And what is it in general? It's going to be some combination of these R's and M's and N's. M minus R is a nice one. How many rows are here? So let's look at it a little bit. How many non-zero rows are here? 2. And they are tied to the pivot columns. And in general, there are how many pivot columns? By definition, in fact, right? Yeah. So it's always true that the basis for row space and the dimension of row space is R. Yes. Let's just arbitrarily add big deals. So the dimension of the row space of A equals the number of rows starting with zero, equals the number of non-zero rows in the reduced row echelon form, which equals the number of pivot columns. Coulombs is different. Oh my God, it's exploding. Brain. I have to wash it out when I get home. Pivot columns, which is equal to R. What a sad little R. Okay, R. Maybe I should do these. See, that's a no, that's not. All right, okay. R, right? So the dimension, so row space and column space have the same dimension. Which should cue like thunder and lightning. Okay. Again, the budget is not what it used to be. Okay. Either of the jokes. Okay, so let's see. So, okay. Have I just mindlessly done this? Okay. Wow. I feel like this is good. This is really good. I totally did. Wow. Lots of writing. Okay, we have more things to find out. That's really, really good. Fantastic. So nutritious. Okay. Good. All right. So huge moment. Well, they're all big moments, but the dimension of row space of A is equal to the dimension of the column space of A. Right. So there's something, an A sends vectors, right? And an A times x equals b, we're kind of getting this idea that this one is in row space. X is in row space. This one is in column space. If it's particular, I'll write p particular. In column space. So we're getting at this idea, the idea that every m by n matrix, this is really nuts, has an invertible R by R matrix inside it. On the inside. Possibly hidden ridiculously. Yes? Not yet. It's a great question. Not yet, because we'll see another great thing happen, and then we'll have... Excellent question. Yeah. And then we'll have a really, really beautiful little clean bit of notation. Well spotted. I am withholding from you again, people, secrets. Okay. Good. Really good. So here's another one. Another cool thing. Great question. Okay, big deal. What do we have to? Number 6, arbitrary numbers. That the dimensions of row space and null space add up, right? So these things both live in, add up to the dimension of Rn. This is, again, where the x's live. Awesome. So the dimension of row space, which I will persist in writing out, of A, equals R. The dimension of null space of A, through much pain and suffering, we're going to figure it out as that. And we add these together. So an R plus n minus R equals, right, so these guys cancel, n. Yes. So these two subspaces seem to be dividing it up, right? They're dividing up where the x's live. So that's good. We have to see how that works perfectly. It really does. It says cue loud organ music and lightning. Okay. Well, let me just write down the last statements here. Obviously, this is continuing on Thursday. So row space and null space neatly, very neatly divide up Rn, where x lives. All right, and so we'll have to be content with this. All right, fine. So more later on Thursday, when we're going to complete this story about row space, and we're going to find out about left null space, which is great. You are free. But you want to ask more questions? What is it? Yes. I'm excited about the void. That's left null space. Thank you.